So hello and welcome in this video, and the topic of today's video is successive differentiation. Okay, which is a very important topic in the syllabus of engineering mathematics at various institutes. So we start with, let y is equals to fx be any function. Okay, this is any function of x, which is of course satisfying all the conditions of differentiation. So we can find the derivative of y with respect to x. Okay, which is known as the first order derivative. Okay, which is known as the first order derivative of y with respect to x. Okay, and since y is a function of x, so dy by dx is again a function of x. Okay, so this is again a function of again a function of x, right? So we continue with this process and we can find out the second order derivative of x, and this is again a function of x, so we can find out the third order derivative. Okay, d cube y over dx cube, and so on. In general, we can talk about the nth order derivative of the function y with respect to n x. Okay, so the process of differentiating a given function of x or any independent variable again and again is known as successive differentiation. For example, we are given, let's say, y is equals to x to the power 5, right? So if you differentiate it with respect to y, with respect to x, so this is coming out 5x to the power 4. So as you can see that this is again a function of x, so we can talk about the second order derivative d2y over dx square, which is the derivative of dy by dx with respect to x. So this is coming out 2x cube, and this is again a function of x. So we continue and we find out some higher order derivatives. Okay, so this is how we can find out the higher order derivatives of any function. Again, this function should satisfy all the condition of different derivative. Means it is differentiable, it should be differentiable, only then we can perform this process and find out the higher order derivative. Now in today's video we can consider some special cases, like our first case is this function, something ax plus b to the power m. So this is our function, and this is the specific form of this function, where m, we are assuming that it is, or you can write it here, that m is a positive integer. Okay, this is positive integer. A and b are constants, or you can say any real constants. Okay, they are real constants. Okay, means for example, a function like 2x plus 7 to the power 10. So here you can see that this is the value of a, this is the value of b, and this is the value of m. So we are talking about the derivative of function of this form. So we begin with the first order derivative of this function, so which is dy by dx, and this is coming out m times. We first perform the derivative with this due to this power. Okay, due to this power. So this is m times ax plus b. Now if then we find out the derivative of this ax plus b with respect to x. So since b is the constant, so it is the derivative of b with respect to x is 0, and we are having a. The derivative of ax plus b is a. Now we find out, and of course this is the power m times ax plus b to the power m minus 1. Now we find d2y over dx square. So this is m times m minus 1 ax plus b to the power, now we are having here m minus 2, and again the derivative of ax plus b produces a. So we already have a here, so we are having now a square. Okay, now if we find the third order derivative, d cube y over dx cube, so this will be m times m minus 1 m minus 2 ax plus b to the power m minus 3, and again we are having a here, so we already have a square, so now we are having a cube. Okay, so if you look at this, so you can identify a pattern. So this is the first order derivative, and in this derivative we are having m here, ax plus b to the power m minus 1 means if you are finding the first order derivative, then you have to subtract 1 from m, and you are having a, or you can say the a to the power 1 here. So d2y over dx square is m minus 1. Now you can see that here we are having m minus 2 since we are finding the second order derivative. So here we are having m minus 2 and a square. And in the same manner you can say that d cube y over dx cube is coming out m minus 1 m minus 2 ax plus b to the power m minus 3 a cube. So if you identify this pattern and if we continue, so we can find the nth order derivative of this function y with respect to x is, so this should be m minus 1, and here we can move up to n minus 1. You can see that if we are finding the third order derivative, here we are having 2, the second order derivative we are having 1. So for nth order derivative, here we are having m minus n minus 1, and here we are having ax plus b to the power m minus n into a to the power n. Since you can see that d cube y over dx cube, we are having m minus 3. Okay, this is m minus 3, this is a cube, this is a square, m minus 2. So if we continue with this, so this is the formula of nth order derivative. Of course, here this m should be greater than n. Okay, this is the case when the power given here is greater than the order of the derivative. So this is how we can find the nth order derivative or differentiate successively ax plus b to the power m. Of course, m should be greater than n in this particular case. Now if we are having we can discuss some more related problems, means some sub cases here related to this particular type of problem. So the case 1 is if your m is equals to n, means the power and the order of the derivative is same. So as you can see that here this formula help us to determine the nth order derivative and n is equals to m. So you can see that here we are having m minus 1, m minus n minus 1. So since m and n are same, so in this case your dny over dxn should be m minus 1, m minus 2, and at last we are having this is up to 1. Okay, this is the product m minus 1 m minus 2. So since when m and n both are same here, if m and n both are same, so they will cancel out each other and we are left with only 1 here. And since m is equals to n, so we are having ax plus b to the power 0, and this is a to the power n. So you can see that this is m minus 1 m minus 2 up to 1. So this is simply m factorial a to the power n, right? So this is a particular case of this formula, and you can have if the case 2, we can immediately discuss this case 2 after this case 1. So if your n means the order of the derivative is greater than m, means the degree of ax plus b or the power of ax plus b, so in this case it is easy to verify or easy to check that the nth order derivative is 0. Why? Because you can see that when m is equals to n, it is coming out constant. So if you again differentiate it, so this should be 0. So if this n is greater than m, means the degree is of the term ax plus b is smaller or lesser than the order of the derivative, so it will be 0. Fine. So this is the another sub case. Now we are having some more standard results related to this. For example, if you are given y as 1 over ax plus b, okay, so this will be ax plus b to the power minus 1. So here this is your m, okay, this is your m. Now if we find out the first order derivative dy over dx, so this should be minus 1, and here we are having ax plus b to the power minus 2, and we are having a in the multiplication. Now we can differentiate it again to find d2y over dx square. So minus 1 is already here. Now next we are having minus 2. So basically we are differentiating this term because minus 1 and a both are constant, so they will remain same. We have to differentiate it ax plus b to the power minus 2 again. So this will be a minus 2 times ax plus b to the power minus 3, and here this is a square. And next is d cube y over dx cube. So this is minus 1 minus 2 minus 3 ax plus b to the power minus 4 times a cube. Okay, so this is the third order derivative. So now you can generalize this using these dy over dx, d2y over dx square, d cube y over dx cube. We can generalize this result for the nth order derivative. Okay, so you can see that if you are finding the third order derivative, you are having minus 1 minus 2 minus 3. Second order derivative, we are having minus 1 minus 2. So nth order derivative, we are having minus 1 minus 2 and up to minus n, and here we are having ax plus b to the power. So in the second order, or you can see from here, first order derivative we are having minus 2, the second order derivative we are having minus 3, and the third order derivative we are having minus 4. So the nth order derivative we are having minus n plus 1. Okay, and here we are having a to the power n. So you can see that here we are having minus 1 minus 2, so in total we are having n negative signs. So you can take this as common, so this can be written as minus 1 to the power n. So once you are taking minus out from each of these terms, so we are having 1 dot 2 dot 3 up to n, and here we are having ax plus b to the power minus n plus 1 and a to the power n. So this can be written as minus 1 to the power n times n factorial ax plus b to the power minus n plus 1 a to the power n. So this is how we obtain our nth order derivative. So this is the case, a particular case when this power is minus 1, while in the previous case you can see that we are considering this m as a positive integer. Okay, so this is how we find the nth order derivative. Now we can quickly discuss some example on this type of problem. So let's say we are given a function, for example 2x plus 3 to the power 10, right? And let's say we have to find the nth order derivative, or sorry, 7th order derivative of this function y. So you can see that here if we write our standard results, so this, in this particular case, the value of a means we are comparing this given function with ax plus b to the power m. So you can easily conclude that here we are having a is equals to 2, b is equals to 3, and the power of this ax plus b is m. So here in this case it is 10, and we are looking for the 7th order derivative. So n is equals to 7. So this is the case of the first type case, means when we are having ax plus b to the power m, and you can see that here we are having m minus 1 up to m minus n minus 1. Okay, so this is m is 10, and we continue up to 10 into 9 into 8. Okay, and at last we are having, you can see from here that we have to continue up to m minus n minus 1. So m minus n minus 1 means m minus n minus 1. So here m is equals to 10, so this is 10 minus 7 minus 1, so this is 6, so we are having 4. So we have to continue up to 10 into 9 into 8 into 7 6 5 4. Okay, so and next you can see we are having ax plus b to the power m minus n times a to the power n. Okay, so here we are having 2x plus 3 to the power m minus n, so this is 3. A to the power n means 2 to the power 7. Okay, so this is the 7th order derivative of this function 2x plus 3 to the power 10, right? Now next we discuss another example on this. So this is something, let's say we are having 1 upon x square plus 3x plus 2, and we need to find out the nth derivative of this function. Okay, so as we can see that here we are having quadratic term in the denominator. So first of all we will factorize this or break this quadratic term as a product of two linear terms. So you can easily find that this can be written as x plus 1 plus or multiplied by x plus 2. So this is the same function. Okay, what we are doing, we are writing these x square plus 3x plus 2 as a product of two linear functions x plus 1 and x plus 2. Now next we perform the partial fractions of this. So you can write this as Okay, so let us discuss this partial fractions of this function here in detail. So first of all, you can write this term as a upon x plus 1 plus b upon x plus 2. So from here you can obtain a times x plus 2 plus b times x plus 1. Now if we put x is equals to minus 2 here, so this gives us 3b is equals to we are putting minus 2 here, so here we are having minus b is equals to 1, or you can say b is equals to minus 1. So next we are putting x is equals to minus 1, so this gives us a into 1 is equals to 1, so this gives us a is equals to 1. Okay, so this can be written as see what we are doing, we are breaking this x square plus 3x plus 2 as a product of linear factors. So this is x plus 1, x plus 2, and we further break it in as partial fractions. So we already obtained the values of a and b, so this is 1 upon x plus 1 minus 1 upon x plus 2. So our function, originally we are given this function, we simplified it using the concept of partial fraction and obtained the partial fractions as 1 upon x plus 1 minus 1 upon x plus 2. So the nth order derivative of this will be same as the nth order derivative of this expression 1 upon x plus 1 minus 1 upon x plus 2, right? So you can further simplify this as, you can write it as x plus 1 to the power minus 1 minus x plus 2 to the power minus 1. So this is the nth order derivative of x plus 1 to the power minus 1 minus the nth order derivative of this. So now we are in this case we are using this formula. Okay, so you can see that for ax plus b to the power minus 1 we are having this formula. So you can see that in this formula we are having minus 1 to the power n factorial. Okay, so this can be written as minus 1 to the power n into n factorial, and here we are having x plus 1 to the power minus n plus 1. Okay, and you can see that here we are having a to the power n as well in the multiplication. Okay, so this is a to the power n, and if you compare this with ax plus b, so you can see that the value of a here is 1. So this is 1 to the power n means simply 1 minus, if we are applying the same formula here, so this is minus 1 to the power n factorial x plus 2 to the power minus n plus 1, and in the multiplication you can see that here we are having a to the power n. So again you can check that a is 1 here, so this is simply the nth order derivative of this function. You can simplify it by taking this minus 1 to the power n factorial as common. So in the bracket we are having x plus 1 minus n plus 1 minus x plus 2 to the power minus n plus 1. Okay, so this is how we can use these formulas to determine the nth order derivative of some related type of functions. Okay, so that's all in this for this video. In the next video we will discuss some more formulas on successive differentiation, and we will discuss some more problems related to the successive differentiation. So thank you.